get lost in the transition, right? In the exchange. So this will actually happen. Evaporation, as you know it, can actually happen inside the water. When that happens, O2 gas goes up, hydrogen gas actually stays in the environment because it's super light, because as soon as this H gets released out into the water environment, it finds a colloid or something to bond to before it can escape it as a gas, because it moves so fast because it's super light. What happens then? You have these colloids all of a sudden become latent with hydrogen atoms, and your pH changes. So, dissociation in the water is a major contributor to the pH. Just by water being water, it changes its pH, which is why most farmers will tell you when you get your pH measured on your soil, it's not always the same. One day it might be, you might have more rain than the day before, and you might have a higher amount of dissociation in your soil than the day before that. So your soil pH might go from 6.1 to 6.6 depending on your rain. So when you go and test it and they give you fertilizer recommendations, they certainly want to know, has it rained recently? What were some of the conditions? Is this soil that you pulled out of the ground a little bit more moist than it typically is? They want to know all that information so that they can calculate the right fertilizer recommendation. Okay? Not so much fertilizer recommendation, but the calcium and liming recommendation to change your pH. Oh, I said that wrong. Well, it's essentially the same thing, because it's not H2O. It's H2O, not H. Sorry, guys. Yeah. H2O. So what happens is they don't break, those oxygens don't go off together. What happens is an OH goes off together and then a hydrogen goes off. And then this happens. I explained that a little wrong. Sorry about that. Go ahead and point that camera over here. It's not H2O. It's H2O, so there's two H's, HH, and then there's an O bonded with it. As the dissociation happens, OH stays together, and then the hydrogen leaves, goes out in the environment, and then gets taken up by the colloid. Did I confuse anybody there? Sorry about that. Okay. This explains it right here. H2O becomes H plus and OH minus, right? Which is also a cation and an anion. Okay. Acidic soils have high hydrogen. Alkaline soils have high OH. You don't even really have to worry about alkaline in Hawaii. It's just so prevalent to have low pH because of high nitrogen levels. Okay? I'm going to move on. I don't want anybody to be confused. I haven't heard any questions in a long time.
What if they just say, I don't have to worry about that in Hawaii because what?
Because your soils are acidic. Naturally.
Water changes the pH.
Water can change the pH. Probably not as much as the release of hydrogens of the plant roots, but certainly can affect. Okay? Here's an example of a pH reading. This will just give you an idea where the numbers come into play. They're not just obscure numbers. pH of 7.0 is water, right? It's neutral. That means that there's an even amount of hydrogen atoms and OH anions floating around in the environment. Even keel. There's not more one than the other. You start to lower the pH to acidic levels, to 6.0. That means that that soil then has 10 times more hydrogen molecules as this one up here. it also means that there are 10 times less OH in the environment for every point that is gone down in the scale. You have to do the math together. So what you're saying is, I guess you do the 10 times 10, right? It's 100 times difference. 100 times more H plus than OH. So it's not just 10 times more OH, there's also 10 times less. So you do 10 times 10 equals 100 times more H plus. And vice versa if you go up. Okay? This all has to do with that logarithm that I told you about, the equation that you don't need to know. Most mineral soils are going to be between 3.5 and 10. So you can have highly acid or highly alkaline. Under humid conditions in the tropics, most pH is going to be between 5 and 7. That's you guys. I would be surprised if you'd ever be in an area that wasn't farmed by sugarcane or pineapple in the last 20 years that wouldn't be between 5 and 7. Arid conditions, the southwest of the United States, no rain, very low weathering. Remember I mentioned something about salt buildup? So in air conditions, you have a lot of salt, which can cause alkaline conditions. Remember I said pH is not consistent. It can change all the time. So James, who cares, right? This is why it's important. What number is this on your homework? Here you go here. Okay, number 7. In your own words, one paragraph. Should be able to knock this out in 3 sentences. Describe why pH is important when discussing fertilizers and nutrients. This is why it's important. Because you see this window right here? This is the window in which this is optimal soil pH range. This is the range in which almost all agricultural soils are at. Okay? Why is that an optimal range? Because depending on its pH, the pH of the environment, certain minerals can be taken up by the plant at optimal levels. So between 6.0 and 7.5 roughly, plants are able to take up the most nitrogen they can. If I stray over to slightly acid and I bring it down to 5.5, which is what most soils would be if you don't address them. So if you went out to your land right now, most likely you're around 5.5. At that range, you're not absorbing anywhere near as much nitrogen as you possibly could if the pH was changed. So the macronutrients are pretty much the same. Here's the dilemma. The micronutrients aren't. So, instead of for a certain period of time during your plant growth having the pH here and then switching it, you really want to find a happy medium between this green zone and this green zone, which is where this green line is, yeah? So, no matter how hard you try, if you have a 6.5 pH soil, no matter how hard you try, your plants aren't going to be able to absorb the amount of iron than if it was a lower pH. Which is okay because it's just a minor micronutrient, and you should be able to survive with that. Molybdenum, all over the place, right? So in your own words for that question, I want you to explain to me why it's important to understand your pH. Why? Because your plants aren't going to be able to take up the optimal amount of the available nutrients unless it's at the right pH. Any questions there? This is huge, hugely important. Can I move on? Okay. Function and deficiency symptoms. All right, now we're going to go through a lot of the nutrients. How are we doing on time? Sorry, I'm thinking about something else. I just got a text from my wife. I forgot to bring the car. I have to drive all the way back to Honoka'a. I drove my truck down. That's just what I do. I drive my truck. And so she's flying into Hilo. She just told me, I'm coming to Hilo. And I just remembered I didn't bring her car with the car seat for the baby. So now I got to leave here, drive all the way up to Honoka'a, get the car, drive all the way back down here and pick her up by 7. Son of a... Blah! It's so frustrating. Yeah, you know, come to think of it, it'd be $50 round trip. I mean, I might as well just taxi it up there. Yeah, it's going to be a lot more than that, right? Yeah, just buy a car seat. Yeah, it'd be cheaper. All right, anyway, not to get off. That's where my mind just went for about 30 seconds. All right, we're going to learn about the functions and the disease symptoms. What's question number 1 on your homework? Right? List all those things. Okay. If you are able to access my email where I send you out a PDF of this, stop taking notes and just use that to do that section of your homework and just listen to what I'm saying right now, because I'll have all this in PDF and I'll get it to you, okay? Does that make sense? Okay. So you don't have to write all this down I'm going to go through for the next 20 minutes. It'll all be available to you, okay? Nitrogen. What is question number 1? Function and deficiency. I had a lot of folks last semester just turning on in the function or the deficiency. I need to know both, okay? The function of nitrogen. Nitrogen promotes the growth of leaves and stems. It gives the dark green color to plants, chlorophyll, energy, and improves the quality of the foliage. Quality, a measure of size, efficiency, and it's necessary to develop cell proteins and chlorophyll. Anybody ever see what happens to a plant when it doesn't get nitrogen? That's right. Why? It can't produce that chlorophyll. Deficiency symptoms, sick, yellow, greening color. We just talked about that. On this side we have, just so you know, corn plants that have no deficiency. This side we have that do have a deficiency. See the difference? Shorter stems, smaller leaves, pale color of the leaves and the flowers. Slow and dwarfed plant growth. Got that? Since all of you guys read your packet, you should be able to describe to me what the nitrogen cycle is, because that's in there. But since you didn't, I'll go ahead and explain it to you. Okay. Nitrogen cycle is probably the most important cycle of any biological cycle that I can think of, because without it you wouldn't have plants, animals, or air to breathe. Okay? So, let's start at the top. Atmospheric nitrogen, which exists as N2, or it can exist as NH3NO, nitrous monoxide, or nitrous monoxide, nitrous dioxide? Yeah. NO2. It exists as a gas. And then gets absorbed by the planet in many ways. First way, lightning bolts. Because of their charge, they create nitric acid, which is it creates a gaseous nitric acid that happens around the thunderbolt or the lightning bolt. After the lightning strikes the ground, the charge disappears, and there's this just chamber of gas that is changed because of the charge of the lightning bolt. That gas will then, because it's heavier than air, will actually go down to the surface and get absorbed by plants and animals. Okay? We're only going down right now. Nitrogen fixation. You have plants like legumes, koa trees, that are able to absorb nitrogen gas through its stomata, sucks it up, brings it into its structure, brings it down to its roots. It gives it to a microorganism on which it has created a special environment within its roots for that specific microorganism. The microorganism then changes it from N2 gas into nitrite. It's then released into the soil environment. As soon as nitrite enters the soil environment, microorganisms then take up that nitrite, play with it a little bit, and then turn it into nitrate, being the most accepted nitrogen source for plants. Okay? So we can go from a gas into the structure of a plant, into a microorganism, which is then released into the soil environment and then taken up by plants. Ammonia gas, NH3, exists within the environment. It can be sucked up by plants straight in through their stomata. Not necessarily ones that are nitrogen fixers. Any kind of plant can absorb that gas. It can bring it down into the soil environment, and where microorganisms can then change it to a plant uptakeable form. Acid rain from pollution. It's a water-soluble form of nitrogen, falls to the ground and goes into the soil environment. Let's talk about going up now. Fossil fuel use, N2, N2O, and NO gas goes up into the environment so that it can be turned into acid rain and then come down, right? You also have denitrification. What that is in anaerobic conditions, so these are conditions where there's no air, like in water, nitrogen will actually change forms and turn into N2 gas and go straight up out of the environment. So only in anaerobic conditions, only in conditions where there is no air does that happen. That is a huge thing when you're talking about crops that are in soil that is very wet. Because soil that is very wet is anaerobic conditions, just like if it was in a puddle. And what happens there is you put nitrogen out to your plant, the soil absorbs the nitrogen and goes into that anaerobic environment where there's no air. Microorganisms consume that material, and instead of making it plant available, it turns into N2 gas and disappears. Only when your soil has great aeration and doesn't have wet feet can you prevent that. Okay? Huge problem for taro farmers, as you can imagine. Okay? Volatilization. Crop is harvested, corn's harvested, and then they take the stalks and they lay them down in the field, and then they get beaten up by the sun and the rain and the environment, and turns into N2 gas and just goes up into the environment and gone. All that nitrogen that this farmer put into the ground to make those stalks to hold his crop, all that nitrogen wasted because it goes up and out. Now, if he was to say, take his corn off the stalk and then till that material in beneath the soil surface, then you don't have this volatilization. Okay? Fertilizer production is a huge problem where they take N2 from the environment, mix it with fossil fuels, and then they produce high nitrogen fertilizers. Well, when they do that, there's nitrogen molecules that are in that exchange that need to go somewhere. They can't bond them with any more oxygens. They just need to go somewhere. Well, where do they go? They go into the smokestack and they go up and out, and there's no regulations of manufacturing of fertilizers to control the amount of nitrogen escaping into the environment. Nobody in the United States is doing anything about that. Why? Because we stopped producing fertilizers in the United States about 25 years ago for the most part. So, you're in countries like Mexico, Costa Rica, Canada. These countries don't have any kind of regulation at all, and it just goes up and out. So what do? We set regulations for us, and then we realize that these regulations are a problem for people trying to make money, so they take those operations to other countries, and then they just pump it out into the environment because they have no regulation there. Okay? There's also a lot of runoff that happens. Let's go beneath the soil surface. Let's see, where do I start? Let's do this one. So, these this guy's sitting next to a steaming pile. So this farmer and his cow and his steaming pile and his crop residues, and this guy, of course, makes waste, right? All go together into the soil environment. There's plenty of ways on which the nitrogen can behave within the soil. Soil microorganisms can then take up this nitrogen and this organic matter and break it down into NH4, which is the ammonia, which is the one of the preferred forms of plant uptakeable nitrogen. It then gets switched with microorganisms to nitrate, and then from there, it's usually taken up by plants. Okay? One of them is supposed to be nitrate. It's this one here. This is supposed to be nitrite. So it goes from ammonia to nitrate, and then it gets taken up by plants. Also, the immobilization of NH4, basically what happens is these microorganisms need nitrogen to exist just like any other plant or animal. So in addition to the nitrogen going through all these phases, they need it to survive. This is a huge, sink for nitrogen, microorganisms in the soil. So where there's a ton of nitrogen that isn't natural up here because of pollution, well, you got to assume that there's going to be a larger population of microorganisms that consume this within the soil environment. You got to worry about what effect that has on all environments. If you're affecting this environment, which affects the amount of and the kinds of microorganisms down here, then these processes that go on can be totally changed, and your environment can be subject to major changes in a very, very short period of time. I don't want to go too much into this, but it's a cycle, right? It goes from top to bottom and then back up again. These materials are gases. They turn into plant uptakeable forms. They're taken up by plants. They either leach away or taken up by plants, and then they turn into gases and go back up. Where in this is there an imbalance? Right? Potential problems that we don't even know what they are. Health, environmental issues. Okay, sources of nitrogen. I just talked about that. Inert gas found in the atmosphere, N2. Nitrous oxide found in the atmosphere, not plant uptakeable. NH3 is ammonia. It's a volatile gas. Please remember the difference between ammonia and ammonium. Ammonia is a gas. Ammonium can be a water-soluble mineral. This is the solid version of this, yeah? So once microorganisms get a hold of ammonium, it turns into nitrite, which is a negatively charged anion found in the soil. It's mixed with microorganisms and oxygen and becomes nitrate. The two asterisks here are the only plant uptakeable form, for the exception of the N2. Like I said, they can suck it up through their stomata and utilize it, depending on if they have those fixation abilities, those nitrogen fixation. Here's when I talked about those nitrate, nitrogen things, well, I just explained this. Ammonium becomes nitrite only when this specific microorganism, this is a bacteria, Nitrosomonas, it's a species of microorganisms, only when that specific species gets a hold of ammonium can you create nitrite. Only when microorganisms of the Nitrobacter, these bacteria species, get a hold of nitrite can it become nitrate. Everybody got that so far? Microorganisms. Can't do it without them. Look at this equation up here. I don't know if it makes sense to you, but we have some ammonium here. Mixing it with some oxygen. We get some nitrogen gas left over. We get nitrite left over. We get some water vapor left over. And then we have this. These two are byproducts, right, of this reaction. We move to the next equation. The only thing we care about is these going over here, right? Well, let's talk about these two here. What happens? They're heavy hydrogen atoms. So, when things go from nitrite to nitrate, there is a massive amount of hydrogen released into the environment, affecting what? Yes. So, acidification happens from these two H plus cations. So, ammonium-based fertilizers, which are very, very common for conventional fertilizers, not so much for organic, they can certainly change the fertilizer or change the pH. So, when nitrogen changes forms, there is that pH issue again. So this has come up in 3 different sections where this hydrogen is released through different processes. This is why pH is a huge problem for people. Ways in which you can lose nitrogen. Volatilization, I mentioned that. It's when the nitrogen turns into a gaseous form through a reaction and then goes up into the atmosphere. If you decide to lime at the same time you fertilize, you're a victim of volatilization. Okay? Because you have those 2 plus ions, those calciums going in, and they're competing with that nitrogen you're putting in. It's really just good to have a pH base that's stable, and then you fertilize. So never, ever, ever lime and fertilize at the same time. Always lime, and then 1 month later you fertilize. Then you don't have any of these issues with pH and volatilization. Moisture, heat, and sun. If I take a fertilizer, a nitrogen-based fertilizer, and I walk out into my environment and I just throw it underneath my corn plants and then I walk away, what have I done wrong? Well, I've put the nitrogen out into an environment that it can get rained on, or even just water vapor from the soil can cause it to become moistened. The sun hits it and heats it up, turns it into a gas, and it's poof gone. And you just wasted every dollar you just put out there. Waste of money. So has anybody been guilty of this? You walk up to your plant, you put fertilizers down, give a little water, and you walk away. It's the worst thing you could do for your plant, especially economically. It's just wasting your money. So if you were to say, put a little nitrogen down and then a